Welcome to the part 5 of my video lecture. In part 1 through part 4 of my lecture, we discuss about the single-phase circuit. In today's lecture, we will start how to derive the inductance formula of a three-phase circuit. The objective of this lecture is to learn the technique of mathematical operation and evaluation in deriving the inductance of the three-phase circuit. To start with our derivation, let us assume that we have a group of conductors at a certain distance to point. We will assume also that a current is flowing in each conductor and it will produce a magnetic flux, and this flux is linking with point P. In preparation to derive the inductance of a three conductors in a three-phase lines, we will first derive the flux linkage and inductance of one conductor in a group, which is the flux linkage between conductor number 1 and point. Our main goal in this lecture is to find the flux linkage between conductor number 1 and point P due to current in all conductors. But the first thing to do is to find first the flux linkage between conductor number 1 and point P due to current in conductor number 1 alone. This means that we will examine and evaluate the flux linkage one by one, considering only the current in each conductor. So to find the flux linkage between conductor number 1 and point P due to current in conductor number 1 alone, we will use the equation of internal and external flux linkage we have derived before. This is the equation of internal and external flux linkage we already derived in part 1 and part 2 of my lecture. As I said earlier, that we will use that equation in getting the flux linkage between conductor number 1 and point P due to current in conductor number 1 alone. And this will be the resulting equation. Flux linkage between conductor number 1 and point P due to current in conductor number 1 alone is equal to 1/2 times 10 to the negative 7 I1 plus 2 times 10 to the negative 7 I1 ln D1P over R1. In evaluating this equation, the mathematical operation is the same on what I have done in part 3 of my lecture. So the flux linkage between conductor number 1 and point P is equal to 2 times 10 to the negative 7 I1 ln D1P over R1 prime. Please play back my lecture in part 3 to see the mathematical operation that resulted to this equation. Since we already determined the flux linkage between conductor number 1 and point P due to current in conductor number 1 alone, therefore the flux linkage between conductor number 1 and point P due to current in conductor number 2 alone will be 2 times 10 to the negative 7 I2 ln D2P over D12. Similarly, the flux linkage between conductor number 1 and point P due to current in conductor number 3 alone will be 2 times 10 to the negative 7 I3 ln D3P over D13. And also the flux linkage between conductor number 1 and point P due to current in conductor N alone will be 2 times 10 to the negative 7 IN ln DNP over D1. In the previous slide, we already determined the flux linkage between conductor number 1 and point P due to current of each conductor. Therefore, the flux linkages between conductor number 1 and point P due to current in all conductors will be the sum of all flux linkages. So the flux linkage between conductor number 1 and point P due to current in all conductors is 2 times 10 to the negative 7 I1 ln D1P over R1 prime plus 2 times 10 to the negative 7 I2 ln D2P over D12 plus 2 times 10 to the negative 7 I3 ln D3P over D13 plus 2 times 10 to the negative 7 IN ln DNP over D1N. In this equation, we will notice that the numerator of all constant terms are the distances of each conductor to point P, while the denominator are the distances between conductors. In that case, it is rational to associate all common numerator as well as all common denominator. We can do that by splitting first all the quotient term. I will show how to split. For example, the first term of the equation, I can say that I1 ln d1p over r1 prime will be equal to I1 ln 1 over r1 prime plus I1 ln d1p. From the rule of the logarithm, ln a plus ln b is equal to ln a. Therefore, the above equation will become I1 ln 1 over r1 prime plus I1 ln d1p is equal to I1 ln 1 over r1 prime times d1p, which is equal to I1 ln d1p over r1 prime. So these two are also equal. After splitting all the quotient terms and then grouping, the resulting equation will be 2 times 10 to the negative 7 I1 ln 1 over r1 prime plus I2 ln d12 plus I3 ln d13 plus In ln 1 over dy1n plus I1 ln d1p plus I2 ln d2p plus I3 ln d3p plus In ln dn. We can say that the sum of current in all conductors is equal to 0. I1 plus I2 plus I3 plus In is equal to 0. Equating In is equal to negative I1 plus I2 plus I3. Substitute the value of in the above equation. The resulting equation will be 2 times 10 to the negative 7, open parenthesis, I1 ln 1 over R1 prime, and so forth. By expanding the current term, the resulting equation is this equation. And grouping the term with the same current or I, the resulting equation is this. Previous slides, we grouped the term with same current and the resulting equation is this. Using the rule of logarithm, these group terms will be equal to this term. So in the writing the equation will become like this. We will notice in this equation, the term in blue color are the logarithmic ratios of distances between conductors and point. Now letting point P move infinitely far away from the conductors so that the terms containing logarithmic ratios of distances from P becomes infinitesimal. Therefore, the flux linkages of conductor number 1 in a group of conductors is equal to this equation. So this is the equation of flux linkage of conductor number 1 in a group of conductors with current flowing in each conductor. This equation will be used as a reference equation for the derivation of inductance of a three-phase lines in the succeeding videos. Thank you and see you in part 6 of my video lecture.